We broke, I showed you some really great examples where we were able to predict the chemistry really well. And so we were feeling really great. But there's a bunch of systems we couldn't do. So we tried to predict some low temperature systems, and the results were not satisfactory. We had trouble with with high molecular weight species. Mostly we kind of overwhelmed the computer with the complexity of the chemistry. We're mostly limited to basically to molecules and reactions that we know a lot about, because then we have very good estimates. And the more we get strange stuff that people haven't studied before, the more our estimates are bad. When our estimates are bad, we build the wrong network, we don't know what's important, and then basically we're in trouble. So it really relies on pretty good estimates. And this is key issue, that if you use the approach used in RMG, which is selecting species based on what has high rates, it really requires you to be able to estimate what has high rates pretty accurately. So you don't need the numbers to 10%, but you do need the numbers at least to order of magnitude. If your estimates are off by more than that, you really have problems. And the worst rate estimates are for the reactions that the humans think are the least important. Those are the ones people spent less time on. But this is a problem. First of all, the humans judged that this was not important, and therefore they never looked into it. Usually the humans are right, but not always. And the fact that they thought it wasn't important, then they never looked at it, it might actually be important, right? They don't know. So we have some examples like that. Another problem is that when you have bad rate estimates, they can be bad in two directions, too high or too low. If it's an unimportant reaction and you estimate it too low, no big deal, because it's just going to tell you it's not important. And if that's correct, you're good. And it'll be omitted from the reaction, from the mechanism correctly. Actually, a problem is sometimes they're estimated too high, and the unimportant stuff gets incorporated into the model, because the computer gets confused and thinks that it's important because the estimate was too high. And then you spend a heck of a lot of time tracking down all the side chemistry resulting from this reaction that you actually is not important. And so you can fill up your model with all kinds of stupid reactions of weird species that are not important. So you can have both problems. You can have a problem where an important reaction is underestimated and you leave it out, and then you don't have the important reaction, and then you'll never get the model right. And you can have the reverse case where an unimportant reaction is judged to be important, and then the computer spends a lot of effort tracking down this unimportant chemistry. And sometimes so much effort that it overwhelms your computer, and you fill up the whole model with all these stupid reactions that don't matter. And we've had both cases. Rate, we judge things based on rate. Rate's important, but it's not the same as sensitivity. And there's some low rate reactions that are important, but have low rates. But right now we're judging which species to put in based on the rate, not the sensitivity. So we get all the high rate reactions in, because that's what the computer's trying to do. But sometimes it might leave out a low rate reaction that's actually important for the overall phenomenon. And this particularly happens in cases where there's reactions that create or destroy reactive intermediates. So if you have like radical recombinations or methods that make radicals, or if you have a catalytic system and you have something that poisons the catalyst, those kind of reactions are really important. But from our algorithm, it would not select them because they would typically have very low rates. And so you would omit these reactions that could be very important. And in combustion, this really comes up a lot in low temperature ignition, where there's lots and lots of reactions that have to be included in order to get the ignition right, but many of them have very low rates, and so they wouldn't be picked up. And then there's a proof, a mathematical proof, that if you make the error tolerance go to 0, you'll get the right model. But in practice, you never can make the tolerance tight enough, because you'll make the model so large that you'll overwhelm the computer. So in practice, you have to keep tolerances that aren't really as tight as you would want, just to be practical. And so it makes it a little bit slightly random about whether you actually included enough reactions to capture everything. So we have a bunch of cases where it worked great, and I showed them to you, but we also have a bunch of cases where we were unsuccessful. A very important concept, regardless of how you make the model, is the idea that kinetic models have a valid range. So if you have a kinetic model and it works for some condition, it's very interesting to know if I change the reaction conditions, would this model still work? And you typically want your model to work over a pretty broad range of conditions, because that way you don't know when you're building the model, you have an idea of what reaction conditions you're going to encounter in the real system, but it's not 100% accurate. So you need your model to be a little bit robust, that it can still work at some slightly different reaction condition, different than what you were thinking of when you built the model. And trying to understand this is really important, and this is a key problem in our community. That right now, when somebody publishes a model, they don't tell you what the valid range is. So they publish a model, and typically they publish like 1 or 2 calculations done with that model for some conditions. So you can assume that they thought the model was good at those conditions because they wouldn't have published it otherwise. So you know 1 or 2 conditions that the author of the model thought that the model worked for. But you really don't know the full range of conditions where this model would be accurate. And maybe the author doesn't even know, right? So nobody knows. So now we have in the literature a model. It worked for some condition. And now you're a lazy graduate student number 17. And you come along and you read this paper and you say, ooh, that has the same fuel in it that I want to study. I guess I'll use that model. And you cut and paste it, and you stick it in your computer simulation, and you go ahead and run. And I would say you basically have no idea if that model is going to work at your condition or not. You're just kind of hopeful that the model is going to work at your condition. And it might, but maybe not. Because the models are always a truncated expression of reality. They always leave out some reactions. Because not all reactions matter at all conditions. So you can get away with leaving out a lot of reactions. But if you change the composition or the temperature far enough, at some point you're going to hit the limit of where the model works and where you need some new chemistry. And combustion, this is famous between low temperature and high temperature, and also between fuel-rich and fuel-lean. The chemistry is really different. And models that work in one of those regimes might not work in the other regimes. And so you just, if you blithely just grab a fuel-lean high-temperature model and you try to run it in a fuel-rich low-temperature condition, you're not going to get a result that's any good. There's some literature to try to understand this. So for example, this paper is like trying to define, given a model, what's its valid range, like how far can you vary it before the model's not going to be good anymore. But I would say that most models, nobody knows what the valid range is. And what happens is people frequently misapply models at some condition that they really can't work at. And then they're disappointed it doesn't work. Or even worse, if it does work for their particular observable, then they mislead the field into thinking this model should be used at this condition. And that can cause a lot of problems too. And again, the accuracy is much worse at lower temperature. And this is because we can't estimate or calculate E's as well as we want, the energies. The barrier heights, the enthalpies, they always have some errors in them. And it's very easy to be off by a few kcals per mole in these numbers. But remember, at room temperature, the KT is only 0.6 kcals per mole. So you really need to be like down to 1 kcal accuracy or better to work at room temperature. And we are very seldom that good. So our estimates usually off by several kcals per mole. Even the really good quantum calculations often are as much as a kcal. And at high T, at ignited flame temperatures, this doesn't matter because the RT is so large, you can get away with a lot of errors in the energy. But at room temperature, it's really killer. And so, there's a lot of chemistry that's important that's happening at room temperature: biological chemistry, organic chemistry, a lot of practical environmental chemistry, and all those fields, you're really in trouble to try to get the predictions. And I think fundamentally, you just need more accurate EAs, and so you really have to work on how can we get more and more accurate barrier heights. So I showed you before some great stuff about how great the isobutanol model was, and it was really great, but it completely missed predictions of how the ignition delay depends on oxygen partial concentration. So here's an example. It shows that we predict the fuel dependence. So this is like phi. When you're changing phi in air, basically what you're changing is how much fuel is there. And so the model predicts that the fuel, changing the fuel increases the ignition delay if you make it more dilute. And it's not exactly in agreement with the experiment, but similar. But then in the model, when you vary the oxygen, we don't predict any change in the ignition delays, but experimentally they see a change. So there's definitely problems, and this is one kind of problem. So even the best models in literature that predict a lot of things really well, like my isobutanol model does, it doesn't predict everything right. And it just emphasizes that these models are very, very complicated with lots and lots of parts in them. And each experiment is only sensitive to some parts of the model. And you can find some observables that will be mispredicted by almost any model. And it's really difficult to get a model that gets everything right. And the low temperature is really bad, right? The low temperature ignitions, the temperature's lower, so the errors are worse. The sensitivities are worse. And you get a lot of polyoxygen species, which have, it makes the whole thing more complicated. You get more floppy modes, you get more expensive quantum chemistry, you have quantum chemistry is not as accurate, quite a lot of problems. When we try to build models, as we showed before, many systems require more than about 100 species and maybe 500 reactions. And the number of edge reactions, the reactions that you could reach in a single step from the species in the model, the number of those species grows exponentially with the size of the model. So by the time you get up to 100 species, you're having quite a huge number of edge species. And if you have things with molecular weight growth, like formation of soot or polymerizations, it's even worse. You get so many species. Usually we have to compute most of these numbers, but the larger the molecules are, the quantum chemistry gets worse and worse. So as I told you, the accurate quantum chemistry method scale is the number of electrons to the 7th power. So if you increase the size of the molecules by like an order of magnitude, it's like you're making the calculations each one 10 million times longer. And so even if, in the best case, that's a long time. And also the transition state searches to try to find the reactions is not perfect. And when you have big molecules, they have more degrees of freedom, and they typically have more saddle points. And it's harder and harder to find them all, to find the lowest one, the one that's really the transition state that controls the rate. And often this needs human assistance, but then this depends on a very smart human to be able to guess the geometries of the transition state that matters. To try to control the memory usage and keep things under control, we've instituted a thing called pruning, where we are building a reaction network. We're considering additional possibilities, but we gradually are determining that certain of the possibilities are just not likely. And so we can prune them, erase them away. At the same time, we're still building the model. So we have this picture here where we're writing down additional species and reactions, and at the same time, we're erasing some of them to try to keep the total number of species and reactions that we're considering kind of under control. Because if we just keep adding, it just blows up exponentially out of control. this can work. You can see you can save memory a lot. So this was like if we didn't prune compared to pruning, you can see that we saved quite a lot of memory. This is 12 gigabytes here of memory RAM we were using before. Now we're down to like 2 gigabytes. That's a lot better. But this is tricky because you might accidentally erase something too soon before you really are sure that it's not important. And then once you erase it, you never considered it again. So it's a little bit risky to do this. But anyway, that's how we do it right now. 2D versus 3D. So most of the algorithms we're using represent molecules as flat pictures, like I drew here, you know, a bunch of carbon atoms stuck in together. In reality, this is a three-dimensional thing. And that three-dimensionality doesn't matter that much, usually, but sometimes it does. So there's certain things about molecules that are like intrinsically three-dimensional, and we just won't capture them. In RMG's estimates, does not aware of the three-dimensional structure at all. If you do a quantum calculation, the quantum is sensitive to 3D because it's working in real three-dimensional space. And it can get it. However, this goes back to the same problem with the conformers, that there could be multiple three-dimensional structures that are all relevant to the same reaction, and you need initial guesses for all of them. And sometimes we might not provide initial guesses that correspond to some of the true transition states, for example. And so we'd only find a subset of all the transition states. And so by Murphy's law, you miss the one that's important, and your numbers are way off. And all this stuff comes up a lot in molecules that have cyclic transition states, particularly cyclic molecules that have cyclic transition states. So the transition state is actually a bicyclic thing. And then there's a lot of three-dimensionality to it. And there's a whole part of organic chemistry that's about this called stereoelectronics, where like the three-dimensional alignment of certain orbitals is very important for the barriers. And we're mostly missing that. That whole thing is missing it right now. And again, you know, if the estimates are way off, sometimes the estimates will be too low. RMG will interpret that as meaning this reaction is not important, but actually it might really be important. And we'll omit it, and then we're doomed. Because once we never consider the important reaction, it's gone. There's not really any easy way to recover this. And it can be hard for the humans to discover what happened when this happened. All right. Now, some people really don't like carbon, hydrogen, oxygen, and they'd like to consider some other elements. I talked to some of you. I heard somebody wanted to work on bromine, for example, fluorine. So suppose I wanted to add bromine or something to my models. What do I need to do? So for example, suppose I wanted to add bromine to my molecules. I need thermo. The Benson type representation is you say, well, I have a carbon atom and it's surrounded by 4 atoms. Here, W, X, Y, Z. And I want to know how many more functional groups would I have to add. So if I suppose I had like if I have these ones, I have carbon, hydrogen, nitrogen, oxygen, and sulfur. How many different functional groups are there? How many different 4 atom things are there that can go around a carbon? You get the idea? Maybe if I just do it with hydrogen, you know, I have carbon and hydrogen, all I can have is I can have 1, 2, 3, or 4 hydrogens here, and the rest would be carbons, right? So there's only 4 possible tetrahedral groups for carbon with hydrogen. If I do carbon, hydrogen, and nitrogen, then I can have each of these slots could be either carbon, hydrogen, or nitrogen. So how many would I have? How many different? Any ideas? This is a combinatorics thing, right? Any ideas?
Would be something like 4 to the power of 5 over 4 factorial.
Maybe, I don't know. Is that right?
I don't know.
I think that if you say, yeah, we have 5 things. So first, the most naive thing, you say, oh, well, there's 5 different possibilities in 4 slots. So it'd be 5 to the 4th power, I think. So that would be 25 times 25, so that's, what's 25 times 25? 625? Okay, so there's 625 possible. In reality, it'd be less, because that I think counts them as in order. So probably 625 divided by 4 factorial. So what's that? 625 divided by 16, is that right? No, 24.
24.
24. So
Almost.
That's about
Almost
125 again.
you think it's about 100? Is that right? No, less than that.
25.
So about 25. Something like that? Yeah. Okay, so there's like 25 different group values that I would want to have here. If I want to add one more, suppose I want to add bromine, then it would be, instead it would be 6 to the 4th, no, yeah, 6 to the 4th power, is that right? Still divided by 4 factorial. Yeah, is that right? I think. So I don't know what 6 to the 4th power, it's bigger than this anyway, right? So you can see every time I add in a different additional element, I add a whole bunch of additional group values I need in order to compute the thermochemistry. And it gets worse and worse the more elements I add. And similarly, the same thing happens to the reaction rates. Because then I have each of these functional groups can get attacked by like an OH. And so there'll be a different rate for each of these different functional groups being attacked. And so I need to get numbers for all those. I have to just say quantum calculation for every single one. And so you can see that the general problem is like as I try to make my computer model more comprehensive to understand all of chemistry, it's can really like blow up of how many different possibilities of what can happen, how many different reactions can happen, and then also all the numbers I need to be able to estimate all those rate coefficients and all the thermochemistry. And so this is like a key problem. And so most people, if you look at models, very often they only have a couple elements in them. And one part of that is that they're keeping the combinatorics down by not having too many possibilities. And the more possibilities you allow, the worse it is. Similarly, if you try to estimate the thermochemistry for something like this, we would use Benson's type method, and we would have different groups for each carbon. And we just add them up. And maybe one for the sulfur here too. Right? We'd add these up. Now, in some systems, for example, suppose there was an OH here. We'd have to have one more group. That's okay. But this OH could like hydrogen bond maybe with the sulfur. And so then there would be like some extra interaction. Normally, we just don't even worry about it. Right? But in reality, it could, and it would change the numbers. And so we should take it into account, but every extra effect like that we add is like another number we need in the model, in the databases, in order to estimate the numbers. And so it really expands quite badly. As you make the molecules more complicated with more elements, each thing you try to do gets more and more difficult. So you'll see in the literature that most of the models are for small molecules, where molecules only have a couple elements, and just try to keep it compact. Then we can actually get a finite number of parameters, and we can estimate everything or calculate everything. And so like a challenge for the future is how to expand. Now, fortunately, a lot of systems don't have that many elements in them, a lot of practical systems. And so we're okay. But of course, the material scientists would love to put more elements in, because that's their thing, right, is elements. They're having a lot of trouble with this right now. They're trying to figure out like how to estimate the properties of alloys, of all kinds of 3 or 4 metals together, and the combinatorics of like all the different arrangements and the different crystal structures they can have. And it gets like really, really large number of things to calculate. Now the computers are getting better, and so that's helping a lot to do this. But there's like this constant thing where we always want to do something that's just to the limit what today's computers can do. And then somebody invents a new computer, and for first year, 2 years, we can make these great advances, and then we hit the limit of the new computer too. And then we have to wait for the next computer to come. And that's sort of the situation right now. But right now, do you guys know the exascale computers? Have you heard about this? Yeah, so there's a couple. Yeah, Jackie probably talked about it, yeah. So there's a couple really, really big computers that this country's agreed to buy, and there's a couple other countries that bought these other really, really gigantic computers, tons and tons of GPUs. And that's like opening up. If you have software that can run on them, you can do things that are like 1,000 times harder than what you could do today. And so for a while, as people figured out how to use those computers and write good software for it, we should be able to make a lot of advances. But then we'll be stuck again. But anyway. All right, to summarize. The predictive kinetics would be really great, really, really helpful for us in doing combustion problems. And it's practical to make fairly accurate predictions of thermo and kinetics to kind of about 1 kcal per mole, maybe factors of 3s in the A factors for kind of smallish molecules. And we can automatically build kinetic models for like these kinds of species up to about 10 carbons, guided by the Benson methods. And then we can do the sensitive numbers, we can recompute them with quantum chemistry to get them better. And at high temperature, we often are quantitative. So we have a lot of cases where we did real predictions before the experiments, and we actually predicted it worked fine. And this is completely different than the idea of fitting to the data, but to actually make a prediction beforehand. But if we want to go to lower temperatures or to new chemistry, we're going to have to do lots and lots of quantum chemistry calculations, and we'll need very high accuracy for the low temperature part. And so this is like I would say kind of like short-term state of the art is trying to figure out how to get slightly more accurate quantum, how to do it for a lot of cases to really establish really good numbers. But I would say overall, compared to what Dirac thought in 1929, we're like way better. That this whole predictive chemistry idea is looking way more promising than it was back in 1929. All right, so that's the end of that slide deck. Any questions about that or comments? Yeah.
Plan or have added like some lumping procedure to reduce the number of?
Yeah, and I'll talk about it later, but yeah, so for a while in my life, I was working on like the model reduction methods and how to, because we made these gigantic models. I was super proud. I had this great gigantic model, and none of the mechanical engineers would talk to me because none of the models were any good for them because they're all too big. So then I had to figure out, well, how can I squeeze my models down to make them usable for the real simulations? And I worked on it. Actually, Ed worked on it a lot, and Tianfeng Liu was his student or postdoc? Student. He was student. Yeah, he was a student here. He made some really nice advances in how to do that. And so my group published some papers. Tianfeng actually made a whole career on doing this. And some other people also made some really nice works on how to do the model reduction. So we have the model reduction methods. I'll talk about them in a bit. They don't really completely beat the problem. So there's a lot of clever ideas of how you can like either kind of use model reduction on the fly to greatly reduce the computer cost of doing the simulation. I think that one works very well. Model reduction is where you completely remove species to try to save memory in a CFD simulation by reducing the number of state variables. That's tougher because you're like actually erasing information when you remove the species. I think it might be possible, but it's definitely it's more of a project to do it that way. So the CPU, I think for CPU purposes, we can do a very good job. For memory, it's like more of a thing to figure out how to do it. But we'll talk about that a little bit later. But it's very important for practice, right? So if I make these models that have, like 600 species, definitely, even today's CFDs, they normally can't handle that. They would say, more than 100 or 200 species, it's like, forget it, I can't do it. So then we have to figure out some way to get together. And also, now there's a huge interest in the sustainable aviation fuels and replacements for diesels. And those are the molecules are big, and the models will be really, really big. In fact, they're so big that I have trouble even to make the 0D models, much less you would not be able to use them in a 3D simulation. It would not be possible. So we have to figure out how to do it better. But I'll come back to that. All right, new topic. Partially premixed flames, diesel combustion soot. So before we talked about premixed flames and diffusion flames, but they're not actually, neither of them is really that popular. And a more common thing is these partially premixed flames. And you guys have probably did it. So in your chemistry lab, you probably used a Bunsen burner. You guys remember a Bunsen burner? So a Bunsen burner, how's it work? It has the fuel comes in, a little bit of air comes into this slot, and the fuel in the air comes up and burns. But it's not enough air to fully burn the fuel. So you have like an interior flame that's a premixed flame from the premixed air and fuel. And then the exhaust from that still has a lot of fuel left in it. It's still fuel rich. And so then you have a diffusion flame where that fuel, that hot, rich mixture gets up in contact with the air and has a diffusion flame. So you have both a premixed flame and a diffusion flame together in one gizmo. And they affect each other. So the heat from that first flame is affecting what's happening in the fuel-rich region here, and therefore affecting what happens in the diffusion flame. And this kind of thing is more stable than a lot of straight diffusion flames, and it's safer than pre-mixing a lot of fuel and air, as we do in a gasoline engine, because you don't have a big volume of explosive mixture. So here you have, the only place you have a possibly explosive mixture is in this little tube, but that's it. You don't have a whole giant piston full of fuel and air like you do in a gasoline engine. And here's pictures of it. You can see the kind of the two flames here. And then depending on exactly how you run it, if you don't put enough air in, you can get a situation where this hot, rich mixture will pyrolyze and make soot. And that's why this turns yellow here, because you're making soot and it's incandescing. It's like, so you see the color. So this is really not so good. You really want more like this, where you have two flames, but you don't actually make much soot. Then you're in good shape. Now, this is particularly important to understand diesel engines, and so I'll try to explain this. This is a John Deck's model for how diesel works. This is like from 1997, and this was like a big advance. So people didn't really understand this, but now I'll try to explain to you. So in a diesel, you have a fuel injector, and you have liquid fuel squirt in. It's like a mist of little droplets of liquid fuel. They're getting squirted in, and they're entraining some air. So this thing is a jet, but it's not solid liquid. It's pulling in some air, the little droplets of high momentum, and their momentum moves the air, and the air comes in. And the air in the diesel is hot because you've already compressed the piston. So this hot air helps to evaporate the droplets. And so then you have the droplets all evaporate, and now you have a mixture of fuel and air from the evaporated droplets. So it's got fuel in it because the droplets evaporated and the fuel vapor is here, and there's still some air because we entrained some air into the jet. Then you get this fuel-air mixture burns, and there's a premixed flame. And it's a rich premixed flame because there's not enough air entrained to burn all the fuel. So we have a premixed rich flame. It burns. Whoops. And then just downstream of that, we have leftover fuel because we burned up all the oxygen pretty much, and now we have leftover fuel, and it's hot. It's really hot because we just had a fire. And so now this region downstream here is hot, fuel-rich stuff, very little oxygen. And in this region, you're going to start making a lot of soot because it's pyrolyzed in the fuel. And so you make a lot of soot, and then you make even more soot because around the edge of this, we get a diffusion flame because this fuel-rich region that's hot gets in contact with the air that's outside, and along the boundary we'll have a diffusion flame because mixed is burnt. So the hot fuel gets in contact with the air, which is actually already hot too because it's in a cylinder, and they just burn up. So you have a hot fire around here, and that fire is adding more heat. So we have the fuel is flowing along with the momentum from the jet, and along the edges is getting really hot from the fire. And towards the end, this thing slows down because it's running, the jet's running up against, it's like losing its momentum to air friction as it's going in. And so eventually it stops, and it just runs up to the air and just burns like crazy. And there's a lot of heat. And in that hot zone, the leftover fuel with no air pyrolyzes all the way, and it pyrolyzes for a while, and it makes a ton of soot. So you make this huge pile of soot here, and then that soot has to go through the flame to get to the air, and in this region, most of the soot burns up. So that's how a diesel works. A little weird. I don't know if that's what Mr. Diesel intended, but that's how it works. All right. Now, so question for you. Many people work really hard to try to improve diesel fuel injectors. There's a whole giant industry, Bosch and other people, work on making these very fancy fuel injectors, and they are made to squirt the fuel at very high velocity and make very little droplets. Why are they doing that? What's your thought? Yes?
Optimize the liquid fuel so that it can mix properly with the oxidizer and get
Okay.
complete combustion, so you can reduce the soot and the
Okay, so yeah, so
temperature.
in light of this picture, if you make the droplets smaller,
Smaller,
and you would
and it
think
can
the-
easily vaporize.
you get easy vaporize. So you'd think that you wouldn't have the liquid go quite so far, it would like evaporate sooner.
Right.
Okay, yeah?
So if it's gonna be very small, then the diffusion of heat is gonna, like, the way it's gonna consume it is gonna be faster. So if it's faster, then some of the pyrolysis reactions may not happen, and it might just,
Okay, so I think these are kind of similar ideas. So you want the drop to be small because then it'll evaporate quickly. You want it to evaporate quickly. One reason is that you don't want very fuel-rich regions to move into the hot zone because they're going to pyrolyze a lot because there's not enough air. You'll make this region, this distance shorter for the evaporation if you make them smaller. I'm not sure if that's good or bad, but you'll do it for sure. How about the speed? Why do they want to squirt the fuel in really hard?
Want to get more air into that?
Want to get more air into it, so yeah.
it's the angle of spread. The better it's spreading, it's not concentrating in a certain zone.
Okay, so there's two ideas. So one is you want to have the really high velocity because you have a lot of momentum, and then you'll entrain a lot of air because the momentum of the liquid is what's carrying the air in. And if you bring in more air, then you'll achieve a higher oxygen to fuel ratio in that region where the fuel is evaporating. Second idea was that you want the spray to be pretty big so that you have, again, maybe getting more air per drop. You want to spread the drops out so you don't want to have so much fuel in one spot. So you want to get better burning. And so, but all those ideas would say that when you get to this point where you have the premixed flame, the stoichiometry would be lower, the phi would be lower, like less fuel per air. So you get closer to stoichiometric. So that's a general idea. You actually don't need to go all the way to stoichiometric, but if you could get down to phi to be less than 2, then typically you wouldn't soot. So that would be really great. So that's like one key idea, is to try to get enough mixing before the flame, before this flame, so that this whole mixture would all be, well, at least here it would be phi would be less than 2. What happens then if phi is less than 2, most of the carbon atoms will end up as carbon monoxide, CO, and not as carbon-carbon bonds. And if it's mostly carbon monoxide, they won't form soot very much. So that's the main idea. That was excellent. All right. Now, why am I talking about soot? If you remember, climate change is our big problem, and that's the big problem in the next couple of decades. But we actually have a short-term problem also, that a lot of people are killed every day by the particulates coming out from combustion. And there's like very strong epidemiological evidence that when there's a lot of particulates in the air, a lot of people die. And not all, but a big fraction of the particulates are related from combustion. And then other ones are actually from fuel, from smog chemistry, which is kind of indirectly from fuel, because combustion makes NOx, which makes smog, and also evaporative emissions of fuel contribute to smog. Now, everybody knows that particulates are really bad, but not all governments are very effective at regulating particulates. So some places still have really, really bad particulate levels, and even places that have relatively good regulations in a lot of things don't always have effective regulations on particulates. But some things are regulated pretty well, and so, for example, the modern diesel trucks in the United States all have particulate filters, and that really reduces the amount of soot that comes out. But there's other parts of the economy and other countries where it's not very regulated. The epidemiology is really clear about this. So these are the 6-city study, New England Journal of Medicine. They measured the particulate level in different cities, and they measured the mortality rate in those cities, and they measured it at many different days with different weather and all kinds of different situations, and there's like a perfect correlation that every day you had a lot of particulates, you could go to the morgue and you see a lot of bodies. It was like very much 100% correlated. So you can see it like this. Similarly, China did an experiment by accident where they, in the old days, the old houses were heated by charcoal braziers and coal burners. And on the cold days, it would be very smoky. But then at one point, I think China was having trouble maybe supplying enough fuel for those things. And they just decreed that if you're south of this line, you're warm enough. You don't need any charcoal. And when we build new buildings there, we're not going to put any burners in, because it's pretty warm there most of the time. South China is pretty warm most of the time. So they said, okay, it's warm by the government decree, and therefore building code says no more burners. And so there's a lot of buildings built with no burners. And so they've got cold, too bad, you just shiver, and you wear a lot of clothes to keep warm. But north of this line, everybody agreed it's cold, and you really need to have heaters in the houses, so they kept on building them. And then when you looked at the life expectancy, people on this side of the line were dying 5 years earlier on average than people on this side. So people down here were grumpy because they were cold, but people up here were alive because they didn't breathe the particulates. So this was like an accidental experiment. And so you can go to right close to the line where the weather was almost the same, everything's almost the same, and you'd have a 5-year difference in the life expectancy on either side. So that's pretty dramatic. So, and it doesn't matter in your politics, this is China, this is the United States, it's all the same. People die when they breathe particulates. Now, some interesting things, people have taken photos inside diesel engines, and when they see that all the diesel engines make a ton of soot, but about 99% of the soot that's formed doesn't come out. So somehow in the engine, the soot particles are formed, but then they burn up. And according to the John Deck model, these soot particles get here, but then they have to go through a flame, and it's really, really hot, and there's a lot of air, and they just burn up. So that's the idea. And apparently that works pretty well, but it doesn't work perfectly. So it's not 100% of the soot burns up, but 99% burns up. Another interesting thing is that people have done isotope studies, and it shows that you can put isotopes in the fuel molecules, and if you put two isotopes in a molecule next to each other, they mostly survive next to each other. And you see a lot of C2 fragments, and later at the end, in the soot or whatever you get out, you see those two carbons next to each other. But if you put them in different distance from each other in the fuel molecule, then they just come out separately. And the theory about this is that maybe this shows that most of the fuel breaks down into C2 units, and then the C2 units reassemble into the soot. That's the interpretation of that experiment. Another interesting thing is if you squirt a little bit more aromatics into a fuel, you'll get more soot. And so the hypothesis about this is that somehow having aromatics present at the moment you're trying to initiate the soot is really important for nucleating the soot. And so if you just have a little bit of aromatics there and they manage to survive the combustion, didn't burn up, they are available to catalyze the formation of the soot. And then the other thing is that I think it's still kind of mysterious. If you have a premixed flat flame, it's fuel and air, it comes, it burns up, and then you can sample at different distance above the burner. And first you see a bunch of benzene, and then a little bit higher up you see some 2-ring aromatics like naphthalene, and then a little higher up you see 3 rings, and a little higher up you see 4 rings, and a little higher up you see soot. And it's like 10,000 rings. And you don't see the 5 rings, or the 6 rings, or the 7 rings. All you see is it goes 2, 3, 4, boom. It's all soot. And when you get to soot, you can't see it anymore because it plugs up your probe. So you can't actually measure it anymore. So you basically 2, 3, 4 can't measure because it's blocked. I think there's no clear understanding of this, but also they see that once the soot is there, the amount of polycyclic aromatics in the gas phase plummets. So maybe somehow these aromatics stick to the soot, or they react with the soot, or they react together to form the soot. Nobody knows. Okay, but that's the situation. All right, so now let's take a break, and maybe what time is it? I think maybe we'll stop here. And next time we'll start with some slides that Professor Hai Wang showed at a combustion symposium about soot, so we can understand this a little bit better. All right, have a nice evening, and thank you.